in this problem, we will work on two parts that are connected together and they are stuck between two walls. Okay, so those two rods are stuck, and what happens is that we increase the temperature. So the temperature 0, where the materials are at rest, is 70°F, and we increase the temperature, so temperature final equal 110°F. And the question is, what are the stresses inside the two elements? Okay, because they will try to expand, so it's pushing on the walls, but the walls are not moving, so there's some stresses inside. The information that are given is, okay, I will just highlight what will be provided to you. The material and the dimensions of the rod. So the diameter one is 12 inches, and the length will be 4 feet, and the diameter two will be 8 inches, and the length will be 6 feet. Okay, let's keep going to the right. L2 is a bit longer. But you can find the information that you will need in your table with the property of materials. So we have the aluminium, 2014 T6 aluminium, this one. In that table, we will go grab the E. We will need the modulus of the Young modulus. This is my 10.6 there. And we will need the coefficient of expansion thermic, the 12.8. So this is my 12.8 there. And same thing for the bronze. So this is the C86-1 bronze. Young modulus 15, and coefficient of expansions, thermic expansions 9.6. So that's where all those data are coming from. They are not provided. You have to find them in your formula, like table of property of materials. So the question for this problem is, let me move that down now that we learn how to use it. Up. So we can write everything else. Let me get that off, and let's work. Remember the questions? What is sigma? Sigma 1 and sigma 2. Before we get to sigma 1 and sigma 2, we have two steps. The first steps will be to find the expansions due to the temperature. So the total delta total, okay? So that will be equal to what? That will be equal to epsilon times L, and the epsilon equal alpha times the delta thermic. It's a uppercase delta. So this is equal to alpha delta T times L. So we have the alpha for both rods. We have the delta T is 110 minus 70 equal 40 Fahrenheit. Okay, and the L, that's the L for each rod. So let's do that. Let's make sure we have the correct units too. So the delta total equal alpha 12.8 for the first one, aluminium, times 10 minus 6, times the delta T, that is 40, times the length, that is 4, but we need to put that in inches, so times 12, and plus the second delta, that will be the alpha, 9.6 times 10 minus 6, times the delta, that is 40, and times the 6 times 12 to get that in inches. So the delta total will be small. We get a delta total of 0.05224. So I know it's not expanding because it can't, but that's what it will have expand if there was no wall. Okay, and we still need to find that value. Step number 2. Let's move that down a little bit. Step number 2, we will use the formula that we learned in the previous examples. That is delta equal to F times L, the force times L, divided by A times E. And what we will solve for? We will solve for the force F, for F. The force F inside, so we have, if we look on the side, we have the big one and the small one. And the force F, there's a force that is pushing on both of them, like the wall are pushing on them because they try to expand. If we cut anywhere, there will still be F. Anywhere there will be F. The sigma will be different because the area is different, but the force will be the same. So what do we know? we know that the delta total, and we know this value, equal the delta 1 plus the delta 2. That will be, so we will find the elongations of each road with the formula of the force. So we have delta total equal the force time the length of 1 divided by the area of 1 time the modulus of 1 plus the force time L2 divided by the area A2 and the modulus A2. Again, what we need to be very careful there, it's the unit. Let me keep continue on that side. So delta total, we found the value 0.05224. The force we don't know, so let me factorize by the force. That's what we try to find. L1, we have 4 times 12. The area A1, the diameter is 12. So pi times 12 divided by 2 square time the module Young, that is 10.6 times 10 at the third. Oh, 10, oops, like this. So this is my L1 divided by the area 1 times the Young modulus of the aluminum plus the L2, that is 6 times 12 divided by the diameter, the area of the second one with a diameter of 8, so 8 divided by 2 square times the Young modulus, that is 15 times 10 at the third. Okay. You play with all of that and you solve for the force and you find a force that is equal to 3.85.3. This is kilopound. This is kilopounds because what was our delta? That was inches. Yeah, because we have on the bottom module Young in KSI. So we have the module Young in KSI, so kilo square per inch square. So we get the force in kilopound. You can check their unit. And that's steps number 3. Now that we have the force and we remember we said that the force is the same everywhere, we can apply the formula that we know since the beginning, sigma normal force, sigma, so the normal stress equal the force divided by the area. So sigma in the road number 1, this is in number 1, this is my number 2. In number 1 equal the force, 385.3, divided by the area, pi time diameter is 12, so 12 divided by 2, 12 divided by 2 square, and the sigma 2 will be 385.3 divided by pi time the diameter is 8, so 8 divided by 2 square. We ended up with the sigma 1 in the first one equal to 3.41 KSI and sigma 2 equal 7.67 KSI. Does that make sense? What makes sense is that sigma 2 is larger than sigma 1 because the area of the road number 2 in bronze is smaller. So just a little summarize. What we did is like we found the informations in our table for E and alpha, the coefficient of expansion, coefficient of thermic expansion. We found the delta total as there was no walls and it can expand, so how much it will have expand if it could, using the formula with alpha delta thermic times L. We solve for the force using the formula for the delta, but this time using the delta equal F times L divided by the area times the Young modulus. So we solve for the force. And last steps, we solve for the normal stress into the road number 1 and the road number 2. And that's it. There's some other examples with 3 roads, but that's the exact same principle. Hope that makes sense. Bye-bye.